Our next presentation concerns the end of life and life cycle of the Sherpack material and will be given by Antonio Dobon from ITENE. Antonio has a Master of Science degree on environmental nanotechnology by the University of Zaragoza and in chemical engineering by the Polytechnic University of Valencia. He is currently area manager of recycling technologies and particle safety, as well as an expert on life cycle assessment of the Packaging, Transport and Logistic Research Center, ITENE in Spain. Antonio has more than 16 years of expertise in projects related to LCA, carbon footprint, sustainability, eco-design and eco-efficiency and recycling technologies at national and international level, providing leadership of LCA-related tasks and as a project coordinator. He has a wide experience as a critical reviewer of LCA studies and is also part of the membership of the Spanish network on LCA, as well as a speaker in the Spanish Technical Standardization Committee on Environmental Management. He is the author of 17 scientific papers related to LCA in high-impact journals like the International Journal of LCA, Journal of Cleaner Production, and Packaging Technology and Science. So, Antonio, the floor is yours.
Okay, thank you very much, Caroline, for your introduction. So, as Caroline commented, I'm Antonio Dobon. I'm the area manager of recycling technologies and particle safety here at ITENE, as well as the LCA expert here at this research center. But please let me make a very brief introduction on who we are and what we do at ITENE. ITENE is the Packaging, Transport and Logistics Research Center. It's a reference research center here in Spain. We are the only one which is specialized on packaging technologies and also in transport and logistics, and we have more than 25 years creating technological solutions and research and development projects aimed at the companies. Okay, so we develop applied research and development for companies mainly. This is our main aim. So please can go to the next one, please. Our research center is composed by more than 150 professionals. Most of them have a PhD on relevant areas related to packaging technologies. Right now, we are involved in more than 90 research and development projects with 7,150 square meters of facilities, including laboratories. And we develop also innovation and technical assistance projects for companies. We have more than 767 customers working with us, and we also develop a very interesting work on testing services, which include also the testing services on the area of compostability that we will show you the short video at the end of my presentation. So we can go to the next one, please. Here we have the main areas of research which we are involved at the research center. ITENE, we work mainly in the area of new materials, nanomaterials, and packaging systems. Well, this is one of the main areas of work. Okay, we are very focused on the development of new packaging materials, and especially those ones which are related to the food industry, and that's why we are here in this project in Sherpack. But also we work on other areas like, for instance, in intelligent packaging, circular economy, and sustainability, which include also the life cycle analysis and so on to calculate the environmental impact of products and packaging systems. We work also in the area of logistics, developing packaging for distribution, and we work also in distribution models and also in urban mobility and intermodality. And in addition, we work the area of security of goods and people, which is very close related to the packaging, especially for dangerous goods. So next slide, please. So this is a summary of the laboratories and the pilot plants we have. The most interesting things from the point of view of project is that we have a specific pilot plans for the development of new materials and processing. We have pilot plans for the modification and the synthesis of additive that we use for Sherpack project for the preparation of the additives that we use to enhance the properties of the Sherpack material. And well, we have physico-mechanical laboratories. We carry out also microbiological analysis and safety tests. Okay, and we made also some tests on packaging assessment, and transport simulation, and the approval of dangerous goods. So we can go to the next one, please. Well, and now it's time to discuss about the end-of-life issues and the life cycle assessment studies that we applied here in Sherpack project. Well, the first thing is to take into account that we have two main proof of concepts developed in the project. One, which is based on paper, MPC, and the PLA blend, as already mentioned by other speakers. And we have also another proof of concept with the integrates, the start grid that was presented by Jeremy in the last presentation. So today I will discuss about the recyclability, the biodegradability, disintegration, and ecotoxicity, which integrates the compostability of the materials, about the ability to use this material also for instance, the incineration facilities. And finally, I will give you some preliminary figures on life cycle assessment results with which we are right now working with. So the next slide, please. With regard to recyclability trials, what we can say is that we carried out two types of tests, one test of disintegration, another one for soluble screening. Okay, there are different steps. Okay, but the good news is that comparing with the reference material, which is polyethylene with paper, the materials developed here in Sherpack, produced by MPC and paper, have had less than 1% of rejects after soluble screening, which is quite good compared to the reference material. And we have also a very good visual aspect of the transit. So in terms of recyclability, I think we obtained quite good results, and it's a very promising material. Okay, so we can go to the next one, please. Well, the important question is related to the compostability trials. Working with, well, as maybe probably most of you already know how compostability trials are made. Okay, there's a specific method for that, and it's the testing of the compostability is comprised by 4 analysis. The first one is the chemical characterization of the material. This is a common chemical characterization. You know, the amount of volatile and dry solids, the process of metals and some hazardous substances, and also an infrared transmission spectrum test. But the most important part is the test of biodegradation, disintegration, and ecotoxicity. But obviously, when we try to apply, for instance, the methods, the standardized methods for compostability to search samples, well, this is a very big challenge, because the main problem is that it's really difficult to carry out a pilot scale analysis in accordance to the industrial compostability standard, which is the N standard 13432, because the amount of sample which is required is quite high. We are talking about 14 kilos to carry out a test. Obviously, this is a very big challenge when you are carrying out a research work. So in Sherpack project, we finally decided to modify slightly the compostability test, and we adopted a new method for small lab scale samples. Okay, and this modified method is based on the ISO standard 20200, okay, which is applied for home compost, okay, which requires less material, approximately 300 grams compared to the 14 kilos which are required for the pilot scale disintegration test according to the European standard. So that with this modified method, well, yes, we can go to the next slide, please. Next one, please. Here you have the set of tests that has been carried out. Sorry, we have right now data for biodegradation, and for disintegration analysis. And for the ecotoxicity analysis, we are still ongoing. We are testing the proof of concept 1 and proof of concept 2. The only difference is just the second one has the start grid. And well, the good news is that the analysis, the biodegradability analysis of the first start-based paper together with MCC provided very good results for biodegradation. The material, the base material for Sherpack is biodegradable. Right now, we are carrying out the work of the biodegradation test with the proof of concepts. Okay. Apparently, the first results we have seems to be quite good. Okay, but we still have to wait a little bit because the biodegradation test takes a long time. Okay, more than 90 days to carry out that work. And with regard to disintegration, where we apply the modified method for large scale samples, provided very good results. Both proof of concept can be disintegrated under the conditions of the ISO standards. In the ecotoxicity, the tests are ongoing. It seems that with the preliminary data we have, it seems the results will be quite good. Okay, so we can go to the next slide. Here you have the details of the biodegradation test that we performed with the base paper and the MPC. The biodegradation test is made against a sample of 100% pure cellulose, okay, and what we test is the production of CO2. Okay, so the degradation rate is calculated with the formula you have on the slide. Okay, and after a certain period of time, we have to reach at least biodegradation degree of more than 90%. In our case, we reach biodegradation degree of rate of 90%, 90%.18, which makes that the material, according to the ISO standard, can be considered as biodegradable. It's a quite good result. So if we go to the next one, please, Caroline. Here you have the procedure for the disintegration analysis. This is the adapted method that we applied for Sherpack, which basically consists in mixing the material for testing together with some bio waste, and we put in a recipient. We put all the bio-waste with the testing material. We move it several times, and we simulate composting conditions in the lab for 90 days at 58 degrees Celsius. And then, after this maturation period, then we put the samples in a sieve of 2 millimeters, and then we check which is the recovered material from the sieve. So we have to find less than 10% of weight in the sieve. So if we go to the next slide, you can see the results that we obtained for the proof of concept one. For the proof of concept one, we achieved a full disintegration after 6 weeks. Sorry, as you can see in the photographs you have here in the slide. And if we go to the next one, we can see that we achieved also the full disintegration of the proof of concept 2 after 7 weeks, so that the material is disintegrated. Okay. If we go to the next one, please. I will explain very briefly the ecotoxicity test. The ecotoxicity test is very simple. It's just to use the material that is coming out from the disintegration test, and we put it on in a small recipient. We put we made sewing, and then we started to germinate some specific types of plants. Okay, so the idea is that to check if with the material obtained from the disintegration test, a plant can grow. So this is the main concept. So if the material is toxic, obviously the degree of growing will be less than with material which is not toxic. So what we try to find is if the germination rate is higher than 90% and the biomass production is higher than 90%. And this is the test which are right now ongoing here at the ITENE compostability lab. Okay. If we go to the next one, I will give you very brief figures on incineration trials. Okay, because the aim was not only to check if the material is recyclable and compostable, we also check if the material, Sherpack material, is compatible with incineration systems. Okay, because in certain countries part of the waste is incinerated. What we found is that the results are quite good. Okay, obviously we are not in the level of gasoline or diesel. This is something obvious, but the low heating value, which is the minimum value for a sample to be incinerated, is higher than most of the waste that usually can find in municipal solid waste, like for instance, like textiles or wood or paper and board that commonly can be found on municipal solid waste. We are not reaching the levels of low heating value of plastics, obviously, but we are quite close to leather and rubber. So I think this is quite good results, and we are above of the minimum low heating value to operate a municipal solid waste incineration, and the minimal low heating value to be considered a paper and board packaging suitable for energy recovery. So we can say that the material of Sherpack can be also incinerated. Okay. So if we go to the next slide, please. I will try to explain a little bit about life cycle assessment. Maybe most of the audience are not experts on on environmental engineering or environmental issues. But I would like to explain what's behind a life cycle assessment. Life cycle assessment is a quantitative tool that is used for the estimation of the potential environmental impact that a product can have on the environment. So life cycle analysis considers all the steps during since the raw materials to produce the product are extracted until the product goes to the end of life treatment, and then the product is throw it away and recycle it and reuse, or finally disposed in a landfill. Okay, and during all these steps, from the raw material extraction until the end of life, we consider all the raw materials that are used, the energy, the water that is used, and then we combine all this information to estimate which are the impacts on land, air, and water. Okay, which is usually called impact assessment categories that represent different types of impacts, and then it's possible to estimate which is the environmental impact of different options, for instance, for packaging systems. Okay, so if we go to the next one, like this, here you have the LCA matrix, which is a matrix that regrows the amount of raw materials, the water used, the energy used, the production of different pollutants in each one of the life cycle steps. And in the specific case of Sherpack, the goal and scope of the LCA was to carry out a quantitative analysis for the potential environmental impacts of cellulosic base materials developed here in Sherpack compared to the oil-based counterparts. Okay. The boundaries for our study are cradle to gate, so that means that we cover all the life cycle steps of the materials, since the raw material extraction until the material goes to the end of life. But right now only we have results from cradle to gate, so that means that we cover in the results that I'm going to present you now, we will cover only the life cycle steps from raw material extraction until the material is ready to be delivered to a plant or to a facility, to an industry that is able to use the packaging materials to protect some goods. Okay, and in our specific case of Sherpack, we decided to use as a reference product a bar of chocolate, okay, of dark chocolate, that can be preserved for one year. Okay, so if we go to the next slide, here you have the different systems that we compare. We have the proof of concept 1 and the proof of concept 2, and also a benchmark which is made of polypropylene and aluminium. It is a classical material that can be used to preserve and protect dark chocolate. Okay. So if we go to the next slide, here you have the system boundaries. As I explained before, we consider just in the results that I'm going to show you today, only a cradle to gate approach. So that means that for certain materials we cover from raw material extraction, and here we include the production of paper, the production of MPC, and the production of starch in case of proof of concept number 2, and also the production of the PLA blend that is used for coating. Okay, so the 3 main materials, paper, MPC, and starch, if necessary, are well laminated, and then the material is coated with the PLA blend. And we consider also the process of grid printing only for the proof of concept number 2. In the case of the benchmark materials, in that case, the polypropylene with aluminum foil, we have the raw material extraction and production. So we have two main materials, which are polypropylene and aluminum. The polypropylene is treated by film extraction, and the aluminum is deposited onto the surface of the polypropylene by physical vapor deposition. So we obtain a laminate. This is the common industrial process for that kind of packaging. If we go to the next slide, you can see here the preliminary results obtained for the proof of concept number 1. So what we can see here in that graph is 5 different impact categories. As you can see the results are presented in relative percentage. So that means that the results are not comparable. For instance, we cannot compare climate change results with acidification, because each one of the impact represents different environmental impact. But what is possible is to check to each one of the impact categories how much influence each one of the life cycle steps and the materials to each one of the environmental impact categories. Mainly what we can see in this graph is that the main contributions to impact are mainly the base paper and also the preparation of the PLA blend. Okay. In the case of PLA blends, mainly because of the power consumption that is required. But it's something that well, we have still to improve, because we are trying to scale up the results from lab to, well, let's estimate the scale up of the power consumption from lab to an industrial scale. Okay, this is something that we are investigating right now. And other impacts which are relevant is that that MPC does not play a very big role on the environmental impact. Indeed, the maximum impact can be reached in freshwater eutrophication, which is around 20% more or less. So MPC is not one of the main contributors to environmental impact of the Sherpack materials. And we have some small environmental credits because of the wastewater treatment on water resource depletion impact category, because of the wastewater treatment during wet lamination processing. Okay, so these are the main results. If we go to the next slide, we can see very similar results to proof of concept number 2. The only thing is that obviously we incorporate environmental impact of starch grid here. Okay, but the impact of the starch grids is not so high. Only on freshwater eutrophication we can find a relatively significant result, but it is indeed still too small compared to other components of the life cycle. Okay, and if we go to the next one, please. Here you have a comparison of the carbon footprint, which is probably the most common environmental impact category that is considered for packaging systems, where we can see that right now our proof of concept, considering preliminary results and the adjustments that we are doing now on the LCA, well, are close to the environmental impact of the benchmark of the fossil-based counterpart. But there is still a room for improvement on the model. So I think these results can be considered only as a preliminary. But the good news that we are in the same order of magnitude of common the current packaging systems, in that case for chocolate bars. So I think it's a quite good result. So if we go to the next slide, please. Here I have a summary conclusions of the analysis that we made. Well, what we can say is that the Sherpack materials are compatible with the recycling systems for paper-based packaging, since we obtain a very low amount of rejects after the summary screening. We can say that also combined Sherpack-based materials, so the combination of Gestar-based paper and MFC, are biodegradable according to the test we performed here at ITENE. And also the Sherpack proof of concepts can be disintegrated in conditions similar to those ones we can find for the home compost testing. And also, if required, the Sherpack proof of concepts can be also treated by incineration, so the material is compatible with the incineration system. And finally, with regard to the end of life, with these preliminary results we obtained, we can say that the carbon footprint of the proof of concepts is close to the fossil-based counterpart. In that case, the PP aluminum foil. So I think it's a quite good results for Sherpack materials. So thank you very much all of you for attending this presentation. And now, Caroline, if it's okay for you, we can show a small video that we made here at ITENE about composting. Okay, where you can show the procedure that we made for the treatment of the Sherpack samples. Thank you very much.
In the Sherpack project, we have developed cellulosic materials with excellent barrier to grease, oxygen, and mineral oil. These bio-based materials are safe for full contact, as well as recyclable and biodegradable. At ITENE, we have tested the compostability of these materials to ensure the biodegradation, disintegration, and ecotoxicity. For this purpose, we have applied a tailor-made protocol adapted for materials within our research and development process, which is of interest when you have a small amount of sample. All this work is aimed at developing new packaging materials aligned with the circular economy strategy of the European Union.